Good afternoon, everyone, and welcome to this next set of talks about the state of the art of long-term thinking and of long-term archiving. My name is Nicholas Paul Brysiewicz. I'm the Director of Development at the Long Now Foundation, and I currently have the curious task of condensing the next and last 10,000 years into the next 8 minutes. So please bear with me if it seems like I'm talking a little quickly. I've got a lot of cool stuff I want to walk you guys through, and I'm excited to get through all of it today. So let's see if we've got this. Perfect. So the Long Now Foundation is a nonprofit here in San Francisco, California, that was founded in 1996 with the hope of getting people to think more seriously about the long term. So for us, in this case, this is the next and last 10,000 years of human civilization. So as opposed to the short now of this conference or of this semester, this election cycle, this business quarter, we're trying to get people to think about this 20,000-year narrative that we call the long now. And one of the advantages of this framework is that putting yourself in the middle of a 20,000-year temporal window like this means you're the inheritors of 10,000 years of art, culture, science, and technology. But it also means that you're in the middle of the story and at the beginning of the next 10,000 years, at an extraordinarily leveraged point where you have a lot of responsibility to be a good ancestor to the next 400 generations of humans that are coming after you. But of course, most people aren't really thinking that far out. And that's where this guy comes in. This is Danny Hillis, who some of you might know as one of the people who was responsible for inventing massive parallel computing. And like so many technologists of his age, Danny realized in the 90s that the year 2000, where they had always thought of the future being kind of out there by the year 2000, that's when all this stuff was going to happen. It was going to come and go in the blink of an eye. And we didn't really have a replacement symbol for the future, something to get people, to inspire people to think long term. And so Danny, being something of a computer geek, thought, hey, I should make a mechanical clock the size of a mountain that'll keep good time for the next 10,000 years and will act as an icon and a symbol for long-term thinking in the future, the same way that the pyramids at Giza act as a symbol of the past. And so this is kind of a wild idea. He started telling some friends of his, and one of the people that got really interested in it was Brian Eno, a British musician of some repute who's known for being a band member of Roxy Music, but then also inventing ambient music. And Brian realized that if you're going to go to the trouble of building a mythic clock on this scale, you should probably also have a mythic bell chime. And so Danny and Brian worked together to hack out an algorithm that would ensure that every visitor to the clock on every single day in the next 10,000 years would hear a bell chime that no human being had ever heard before and no human being would ever hear again. So that's about 3.65 million unique bell chime sequences that are programmed into the clock. And that clock is now currently under construction inside of this mountain in West Texas. They've been building this thing for most of my adult life, and it's still under construction right now. Rumor has it might be done within my lifetime, but we've never actually offered up a completion date for it. But I did bring a really cool video to share with you really quickly about some of the installation work that went on with the the chime winder, or sorry, the bell chime generator and the clock winder last year. And it does have some sound. So the clock is currently under construction, but that's not the only way we can get people to think long term. For some people, the clock resonates, and for other people, there's other ways we should be reaching them. And so we have a host of other projects. One of the other personalities that got involved with the Long Now Foundation early on is Stuart Brand here, a counterculture figure, American author, started The Well, published the Whole Earth Catalog. Stuart thought that if you're going to go to the trouble to bury a clock for somebody to find in a few thousand years, you might want to put something with the clock that would get them inspired about this discovery. So what kind kind of cultural things could you put there? Mostly he was thinking about a library. He was thinking of something where we'd have all the books that you would need to jumpstart civilization. So specifications for how to make good steel, Socratic dialogue, Shakespearean sonnets, the whole works. You'd want to put this together and have it there for somebody to find with the clock. But of course, you get into these language questions really quickly when you start thinking about a project like this, which is, do you put Borges in the library in Spanish? Do you put Dostoevsky in the library in Russian, or do you just put the whole thing in English, or the whole thing in Mandarin? We start asking these questions about what kind of languages people are going to speak in the future. And one of the languages they're not going to speak in the future is one that's gone extinct. So the Rosetta project was one of our early projects that was designed to collect data and documentation on as many languages spoken on the planet as we could. And when I say documentation, I mean dictionaries, grammars, vocabulary lists, parallel text translations of Genesis, or the Universal Declaration of Human Rights. And then we worked with Lawrence Berkeley National Lab to use a focused gallium ion beam that can etch nickel discs like this one at the 7-nanometer scale. So the disk you're seeing behind you is a little bit bigger than your hand, and it has about 15,000 pages of language documentation etched into it. Of course, this is an homage to the original Rosetta Stone, and each page is about 5 human hairs wide. So rather than actually encoding data digitally, we've actually just have a human eye readable format. It's very small, but a jeweler's loupe will get you there. About 100 times magnification, you can read the whole thing. In 2016, with the help of the European Space ESA, we were able to land one of these archives on Comet 67P. And then this summer, we landed one on the lunar surface as well. We also have a bunch all around the planet because in archiving, there's this idea called LOCKSS, L-O-C-K-S-S, which stands for lots of copies keep stuff safe. And so we have about 100 of these all around the globe. And of course, if you're going all the work to protect languages, the question is, well, could you protect and preserve species? Could you use current genomic technology to de-extinct species that have gone extinct, like the woolly mammoth or the passenger pigeon? So we have the Revive and Restore project, which is working on that. We also invite experts to come talk about their work in the context of the next and last 10,000 years once a month here in San Francisco. Here are some of the people that have talked for us just in the last couple of years, but we have about 230 talks now at this point. Of course, there's a membership group around Long now. It has about 11,000 members across 60 countries. And then we decided we needed a physical place to congregate, so we turned our headquarters in Fort Mason Center just down the street into the interval where we have talks. We have some prototype parts of the clock. Of course, we have that library I was talking about. And it's also an award-winning cocktail bar. We regularly grace a number of top 10 lists in San Francisco and across the United States. And the idea being that you would go with a friend, go have a cocktail in this unusual bar surrounded by unusual objects, and you'd ask yourself the really important questions for being a good ancestor about the next 10,000 years. Like, how can we be better ancestors? Of course, on long time scales, anticipating future need becomes very difficult. It's hard to tell what people in the future are going to need and how you're going to get it to them when they need it. So archiving projects like the one that was announced this morning and like the other ones you're going to hear about today, these archiving projects are the best bet we've got at providing future people with the resources they might need, possibly. And so we're very excited to be part of the advisory team for the GitHub Archive Program. And I'm very excited to introduce our next speakers, which are Patricia Alfheim and Bendik Bryde of Piql.
Good afternoon, everyone. So we are Piql from Norway. We're also the founders behind the Arctic World Archive that you saw this morning. So today we are going to talk about our approach to the challenge of taking care of information into the perpetuity and how we use simple means of technology to ensure the access of that data. So what you see here, this is our claim to fame. This is our core competence. It's a digital time capsule. We call it the Piql Film. So it's an offline storage medium. It's what we call write once, read many medium. So it's information cannot be hacked, the information cannot be tampered or taken away, changed on that storage medium. When we started out, we wanted to design a storage medium that could last for centuries and even thousands of years. And coming from the film industry, we saw there was some properties with the film, knowing that the history of film is more than 100 years and had very good characteristics of how to keep information for the long term. And so what we did is to do that with digital content and to be able to put that on the robust medium. So there's a few important aspects. So in terms of authenticity, so in the digital world today with deep fakes and similar kind of emerging technologies, how can we really ensure authenticity in a 1,000-year perspective? So from our point of view, we think the best way would be to keep the true original of that file and keep it on a very long-term storage medium, not migrating that information, not changing it from format to format. In order to do that, we also need to be able to future-proof, to ensure that we can access and read back that information in the long-term perspective. And we're doing that by using open source software and putting that documentation on the storage medium itself. And that brings us to kind of the most important part that we say that is self-contained. So we are putting all the information about the decoding software, about the file format specifications, about everything you need to be able to retrieve the information in the future in both a machine-readable language, but also in a human-readable language. So it kind of gives the future users the opportunity, without us knowing kind of the knowledge that we have in the future, the software or the computing platforms, still the opportunity to have several options of how to read back the information. So it could be like a low-tech visual proxy, so you can just read information by using light. It could be that you're using the source code to reconstruct a decoder for a file format the knowledge is lost. We even include the file format specification to help that process if the compiling of the source code is difficult in the new system. And we are now also including a virtual machine to help the process of the recoding and rendering of the files for the most used common file formats for preservation today, to make that retrieval process faster and more cost efficient. So what you see here, this is the storage medium. So you see there's a visual frame on top, and there's a digital frame at the bottom. So we're using an optical readable 2D barcode. So we have developed a very flexible barcode that we called the boxing library. So this is written in the C language, is open source and published in our repo on GitHub. So the idea of using the C language was that it's been used for a long time. It's quite simple and very fast, and it also doesn't have a lot of dependencies around it. At the same time, to be able to so we are dispersing the files through a lot of these frames, but to be able to kind of put that together and organize it, we also developed something we call the archival file system. So the archival file system is also open source, written in the C language, and it has a table of content, which makes it possible to understand both the visual file and the digital file, and it understands the file format and can point directly to that specific file format decoder, which is stored on the medium for the retrieval. At the same time, we're storing this table of content both in a human-readable and a machine-readable format. So we think this combination of the visual and the digital really creates an extreme resilience to the long term of the storage. What you see here is, so we're also including metadata representation information in both formats. So what you see here is what we put on the deposit for the GitHub. In this case, that could be a mission statement. It's a file format specification of deflate and gzip, which was used in this deposit to store the source code on our storage medium in the Arctic World Archive. And then, so how can we retrieve the data? So today you can use a data scanner. So what you see here on the right side is the Piql reader. So this scans the frames and then converts it back to the original file. But we also wanted to create the opportunity to get the information back with just the most simple means. So by us, as we've seen, kind of including the information about the decoding software, the archival file system, and the file format specifications, you are able to get back the information just by using a magnifying glass, some kind of a capturing device like a camera, and a computer in the future to retrieve that information. And if you want to understand more about the software tools that we're using, please check out our repo on the GitHub site. So now I'm just giving it over to Patricia.
Thanks, Bendik. So you saw in the video this morning, the GitHub Arctic Code Vault is set inside our vault, which is called the Arctic World Archive. It's located up on the remote Norwegian Arctic island of Svalbard, and it was opened in 2017, so quite young. The vault itself is inside the decommissioned mine you saw on the video this morning, and the region is a demilitarized area regulated by an international treaty, making it a super safe and politically stable area. It's not somewhere that's affected by natural disasters, and it offers the best conditions for storage of film-type medium or a polymer-based medium. So the vault itself is cold, dark, dry, low on oxygen, and which is great because that means no electricity to store this data for perpetuity for hundreds of or thousands of years, making it super sustainable, which is really important, and also actually extends the life of the film as well. And to be able to accurately predict how this medium will survive over time, we've done a number of different testing on it. So the key one being accelerated aging, which uses temperature to simulate the aging process. It's an ISO standardized process, and it takes a really long time. So we're 7 to 8 years into the testing process of this, and we've passed the 750-year mark for readback if it was stored at room temperature. So that dramatically increases the colder and the drier the conditions. So we can say very confidently that in Ava, the data is going to survive for 1,000 years at least, 2,000 years. We're going to continue testing, see how far we get, but we've proven readback so far. We've also conducted numerous stress tests, both from the medium and individual frames, to see how it behaves after lots and lots of reading, how it handles wear, scratches. We've even exposed it to quite a lot of radiation, just to see how it went, and it's proven to be an incredibly robust and resilient medium, which is great, because then we've got a very safe and secure place in the Arctic Circle, and we've also got a really robust medium. Perfect combination. So since the Arctic World Archive was opened in 2017, we've had more than 30 global deposits, with more happening all the time. Quite a lot of institutions want to make deposits of their valuable data and safeguard their piece of world memory while we build a nice picture of the whole. So this is growing all the time. UNICEF this week announced that they're making a deposit. We've got the Vatican Library, the European Space Agency, the Norwegian National Museum, national archives from several countries, corporate institutions, contemporary visual sound art, scientific breakthroughs, political histories, and many, many others. And as I said, growing all the time. So it's an absolute pleasure for us to formally welcome GitHub and its archival program into the Arctic World Archive. As digital preservation enthusiasts and open source nuts, we think it's really crucial to have open source as a core part of preservation for perpetuity, and it's the premise that we've built all of our technology on. So, and it's nice to be able to say that as we've published our code for how to retrieve and read back data in GitHub, now GitHub's depositing their source code in the Arctic World Archive. So really lovely circle. So yeah, to finish off, I'd just like to formally welcome GitHub into the Arctic World Archive community. It's the first software deposit, which is a really unique and valuable part of World Heritage. So thank you.
Please give a round of applause to Patricia and Bendik of Piql. Next up, we have Ioan Stefanovici of Project Silica from Microsoft Research.
Hello. So I'm Ioan Stefanovici. I'm a researcher at Microsoft, and I'm going to talk about Project Silica. So last week at Ignite, Satya talked about our collaboration with Warner Brothers, whereby we stored the classic 1978 film Superman inside a piece of glass. And our partnership with Warner Brothers really reinforced to us the importance of the so-called third copy of your data. So the third copy is essentially a copy of your data with the property that if all else fails, you want to have the guarantee that you can always go back and reread and read the third copy and be able to safely recover your data. And of course, there are a lot of different types of data for which we want this property. This morning, Nat Friedman talked about the importance of preserving source code, right? Think about the millions of people years worth of developer time and effort that's gone into building and debugging the systems that we have today, right? It's a legacy that we want to be able to preserve for future generations, right? As well as Wikipedia, the Internet Archive, effectively the sum total of the world's knowledge. Of course, there are many other business areas where this is also crucially important. And on a personal level, right, think about the number of photos and videos you have on your phone of cherished moments from your life that you want to be able to safely hand down to your descendants. Now, the bad news is that existing storage technologies are inadequate for this. The vast majority of data today is stored on hard disk drives and tapes, which are magnetic media. And the problem is that over time, the media degrades. And so you get failure modes like bit rot. Or in the case of optical disks, media rot. And this is example of what that actually looks like. So this is a laser disk from 1986 that was storing the BBC Doomsday Project, which was a census of the UK with a bunch of other information. And this was supposed to be sort of future-proof way of storing this information forever, and it's now in the digital obsolescence section of the Cambridge Computer Laboratory. And so the way to counteract this problem with existing technologies is to essentially copy the data over every few years to a new generation, to a new device from the same type of storage technology. And of course, the problem with this refreshing of data every few years is that there's a huge financial cost associated with keeping long-lived data around. And increasingly, as the amount of data we have grows, there's an increasing energy cost as well to doing this, which of course is not great given the other environmental challenges that we're dealing with right now. And so in Project Silica, what we aimed to do is to create a storage technology that solves these problems and gives you the guarantee that you're going to be able to store your data safely for thousands of years. And then we want to leverage the economies of scale of the cloud to be able to offer this as a service to businesses and consumers. And the media for this is glass. And I'm not talking about any sort of exotic type of glass. It's a pure form of glass called fused silica or quartz glass. But its raw material is sand. It's very low cost to manufacture at scale. And it has a lifetime of tens to hundreds of thousands of years. And it's a very resilient media, and I'm going to show you in a second exactly what I mean by that. So this is a worm media, write once, read many. And it's very persistent. So what I mean by that is that in order to write data, what we do is we make permanent changes to the physical structure of the media. And so what that means is that once data is written in it, it does not degrade, or it doesn't change physical structure in any way. So there's no bit rot, there's no media decay, which means that we don't need to scrub the media. And of course, the consequence of all of these properties is that we can now afford to leave the data in situ. So once written, we don't have to keep moving it over every few years to a new device, which means that we don't have an accumulated energy and financial cost. And in addition to that, we are less prone to suffering from data loss while copying due to hardware or software bugs. So I'm sure if you talk to any archivalist, they will tell you that this is one of the main concerns, is that when you copy data over, often what you end up with is bugs either in hardware or software that cause you data loss. So I want to share with you a quick video to kind of show you just how resilient of a media glass is, and kind of give you a sense for why it's important to understand these things from an operational perspective in terms of how you might use this in a data center. So water and humidity has traditionally been a very big problem for archival media, in particular ferromagnetic media. As you can see here, glass is waterproof. It is resistant to electromagnetic, to magnetic radiation, which means that in the event of things like solar flares or solar storms, your data is going to be safe. Because we store the data inside the bulk of the glass material, that means that surface level scratches or physical interactions are not really a problem for us. And you can even bake it, and you can even use a flamethrower on it, but we didn't have time to be able to include that in this video. The takeaway there, though, is that if you have a fire in your data center, for example, you can put out the fire with water, even in the worst case. You can always replace your electronics, but at least you have the peace of mind and the guarantee that your data is going to be safe. So how does this actually work? Well, in order to write, we use a femtosecond laser. So this is a pulsed laser. The pulses are on the order of hundreds of femtoseconds. So that's 10 to the minus 15 seconds, just for reference. And what we do is we focus the laser beam inside the bulk of the glass material. And at the point of focus, we get these little voxel nanostructures that are made of these parallel nanoplanes. And by changing the amount of energy that we put in, we can control the depth or the strength of these voxels. And by modulating the polarization, we can change the orientation of these voxels. And so these are two dimensions across which we can encode multiple bits of data. And of course, we can write the voxels in X, Y, 2D planes, and then we can stack them in Z across hundreds of layers. And so in a piece of glass, you're really getting volumetric storage because you can effectively fill the entire piece of glass with data. So this is a video of one of the write heads in our lab back in Cambridge in the UK, writing Superman. Well, you can't see anything because it's being written in infrared, but you can see the glass substrate moving back and forth as the data is being written. And you can see the 7 different beam lines and the little round things at the top that hold the lenses that focus the laser light inside the glass substrate. So to read it, you use a totally different technology. You don't use a laser. You use polarization microscopy. And so the light source for that is a simple LED. And the read head effectively has optical elements to focus the light on the desired sector, and polarization components. So now we get to how do voxels actually store data. So when polarized light passes through a voxel, the voxel will change its polarization across 2 dimensions. One is phase, and the phase is changed based on how deep or how strong the voxel modification is. And the second is angle, and the polarization angle will be changed based on the physical orientation of the voxel in the glass material. And so those are the 2 dimensions that I mentioned during the write process that you can modulate. And so effectively, in order to read the data back, what you do is you focus on the layer that you're interested in. You shine light with a known polarization into the medium, and then you effectively measure what is the change in that polarization that each voxel imparted on the light. And to do that, we use machine learning techniques, state-of-the-art computer vision techniques. And in the picture that you see there, that's an actual picture of data read from one of our samples. And we use machine learning to extract the symbol values that were encoded. Of course, we also use error-correcting codes to fix any residual errors from the raw reading process. And using these techniques, I'm very happy to say that in the past, in less than 3 years since the project has been going, we are now the densest optical storage technology in the world. So with that, I'm going to wrap up. Have a look at our website if you want more details on the project, if you want to read a paper about it. And if you want to work on the coolest storage project out there right now, join us. We have a number of career opportunities. We have a number of SDE roles, postdoc researchers, internships. So come talk to me or send me an email. So yeah, thank you.
Thank you, Ioan. Next up, we have Henry Lowood of the Stanford Libraries.
So, as the Harold Hohbach Curator for History of Science and Technology Collections at Stanford University, I'm responsible for collections, projects, and programs, notably the Silicon Valley archives and a bunch of initiatives on software history or preservation. The Silicon Valley Archives is the world's greatest repository of materials related to the history and development of Silicon Valley. These collections include documentation in every format, including historical software. This is all good, but in the immortal words of James Stockdale, who am I and why am I here? For starters, I've been engaged in software history and preservation for a long time. Here's the invitation I received almost exactly 30 years ago to attend the first conference on software preservation held in early 1990. In 1997, Stanford acquired the massive Stephen Cabrinetti collection in the history of microcomputing, here being used by students in the Department of Special Collections at Stanford. This was probably the first institutional acquisition of historical software collections. My definition for massive, by the way, is 1,375 linear feet of software, hardware, publications, and documents. That's more than 4 football fields of archival boxes, end to end, and it's just one collection. This is what you'd find in some of the boxes. I think you get the point. My curatorial work takes me to artifacts like floppy diskettes and to data cassettes and other formats back to the 1970s. Nearly 20 years ago, in 2000, I co-founded a project called How They Got Game. This is a hub for projects in game and computing history, as well as software preservation. So back to the question, why me? Well, I work on software heritage, both as a curator trying to save it, and as a historian writing about it. Next question, why GitHub? A few years ago, I worked with a team at UC Santa Cruz to develop a unified approach to preserving what we called cultural software objects and their development histories. We coined the term cultural software objects to express the importance of software for critical and historical studies. We simply cannot understand the late 20th and early 21st centuries without accounting for the design, production, and impact of software. As we said in our white paper, future scholars and designers will need well-organized and viable archives to understand the history of cultural software objects. Open source software is a critical component of our software-driven world, and GitHub hosts millions of code repositories. It is de facto a significant archive for cultural software objects. What is documented by software in GitHub? Besides the obvious answer of software development history, let's consider some other examples. The Virtual Apollo Guidance Computer Project supports computer simulations of the onboard guidance computers used in the Apollo program's lunar missions. Clearly important for the history of technology generally. The code repository for this project is on GitHub, but a full accounting of the project includes other documentation, such as issues posts, or of course the project website. Researchers need access to context and documentation found outside GitHub to fully understand the code deposited inside GitHub. Business history is another area in which GitHub-based software has played a significant role. Bitcoin and Airbnb provide two examples. For business-related projects, we again depend on access to external resources to better understand these projects, and we may run across restrictions that limit access to code and documentation. Documentation is also deposited on GitHub. For example, the US National Archives and Records Administration, NARA, put its digital preservation framework on GitHub for public comment. This framework presents preservation action plans for a variety of digital record and media formats, such as email or audio files. Museums have also jumped into GitHub. Cooper Hewitt is the Smithsonian's Design Museum. They've made approximately 75% of the documented collection available online. Their GitHub account is full of, and this is quoting them, tasty bits and tools that we use, including metadata, concordances, and the Cooper Hewitt typeface. And finally, an area close to my own heart, entertainment, notably computer games. Free Doom is particularly interesting for my own research on player-created content. Based on source code released by id Software, it lets players run the huge catalog of mods, replays, and speedruns created over the 25-year history of Doom. Now the last question, my last question. Why Stanford? What can we contribute to the GitHub archive? Well, in a nutshell, Stanford will produce curated collections documenting selected GitHub projects in depth. These collections will include code, but only begin there. Code alone is not enough. We will dive in beyond the code repository to harvest contextual documentation that historians and others will use to make sense of these projects and their impacts. We will include documentation harvested through GitHub features such as issue tracking and wikis, but also external websites, media, and blogs. In order to make this documentation discoverable, we will add metadata and provide access, interpretation, and preservation for these collections. The next few slides introduce the IT environment that will support this project. We start with two robust preservation systems, SDR, the Stanford Digital Repository, and LOCKSS, you already know, lots of copies keep stuff safe. Both of these were developed at Stanford. We're investigating strategies for capturing digital objects for GitHub project collections and may end up using a mix of methods. A quick shout out here to our friends at the Internet Archive for the Heritrix web crawler, which is our go-to for capturing website content. If we go with locks to preserve GitHub assets, we will be relying on a community or network approach based on peer-to-peer verification and polling to identify and correct errors over time. We need a minimum of 3 partners to perform these data integrity checks. The SDR is the other preservation service at our disposal. As you see here, it involves multiple layers and services for management, access, and preservation of ingested objects. SDR assets are discoverable by Stanford's online catalog called SearchWorks, which is available on the open web and exposed to the usual search engines. Digital documents and software assets are accessible via SearchWorks. By the way, Stanford was a project partner in preserving virtual worlds, a pioneering project sponsored by the Library of Congress about a decade ago. This project produced a few collections around historical game software, such as the Doom collection that you see here. The connection here with GitHub-based FreeDoom, which I mentioned earlier, is one of several links between Stanford preservation projects and GitHub repositories. Collection pages with permanent URLs lie behind SearchWorks access. As this example of a Perl page shows, we operate a repository for preserving code and data produced by Stanford research projects, which might be a useful option for GitHub project collections. Finally, an end product for this collaboration could be online library exhibits that interpret GitHub projects. Spotlight, which you see here, is Stanford's application for showcasing digital content in easy-to-produce exhibits. Metadata added to the digital content we ingest from GitHub and other sources will activate search and browse features in Spotlight to help researchers, students, and visitors to interpret the history of these projects. Well, that's it. If you have questions about Stanford's role in this important project, please feel free to contact me via email or Twitter. Thank you very much.
Thank you, Henry. Next up is Roberto de Cosmo of the Software Heritage Foundation.
So hi, everybody. I'm very happy to be here. I'm a long-time computer science researcher, hacker, developer, open source advocate, and today I'm here with my head of director of software heritage to tell you about what we are going to do together with GitHub. But let me start from a first point. We were all talking about software. Software is fundamental in our world. It powers our industry, fuels innovation. It's a pillar of modern research. It's an essential mediator for access to digital information. But as we know well, as developers, software doesn't come out of the blue. It is written by people. And not only written by people, but also written by people for other people to read. It's a very special kind of knowledge, actually, which is human readable and machine executable. When I was a student many years ago, too many years ago, I was using a book by Harold Abelson, The Structured Interpretation of Computer Programs, where you find this phrase. Programs should be written for people to read and only accessorily for machines to execute. Well, of course, you can say this is a professor telling their students if they turn in homework they cannot be read, then they will get a bad grade. But it's more deep than this. I mean, the person that can read a piece of software should be able to read a piece of software. Maybe you next week when you need to fix it. Well, when he was writing this many years ago, there was not much source code available to showcase. Today, 30 years after the beginning of the free software movement, we have an incredible amount of software available. Here, for example, you get an excerpt of the source code of the Apollo guidance computer, and you see, even if you are not yet familiar with the assembler that I'm showing here, you can read the comments, and you see that these people were actually very, very, very careful in programming. Actually, this is a part of the module that is asking the astronaut to turn around the lunar landing module. And you see the programming is very careful when you get the message that say proceed. I mean, the astronaut pushes the button saying, OK, I have turned the lamp around. Well, the programmer just checks if he's lying. I mean, you jump back and check if the antenna is right in the right position. But then there are other jewels. We heard about the Doom, but you remember John Carmack, the incredible developer, he also wrote Quake 3. If you remember, one of the ancestors of Call of Duty, which too many people, including my kids, spent too much time on. And this is an incredible routine which was embedded in the source code that allows you to compute 1 over the square root of x in a particularly sophisticated way by avoiding all floating point operation. I will not read the comments because some of the comments are forbidden to less than 18 years old, but I mean, you can just check it out offline. My slides are online, by the way. As Len Schuster wrote in a beautiful piece of article some years ago, actually source code is an open window in the mind of the developers. And so it's an important asset, and we need to keep it, because even if you are not able to run the binaries, we can still read it and learn things by reading it. Okay, but unfortunately, this source code is a precious asset. Otherwise, we would not be here, but it's also an endangered heritage. If you look at the past, there are many key people who developed the technology we are using today who are passing away, and we are losing their knowledge. At the same time, if you look at the future, software development is skyrocketing. Actually, looking inside our archive, we can tell you that the amount of original content developed around the world doubles every 2 years. And yet, we are missing key elements today. We are missing a global catalog. I fully agree there is a lot of interesting software on GitHub, but there is also a lot of interesting software which is not around GitHub. And software moves around, it changes names, and project starts and finish and disappear. And then we miss archives. I mean, who remember Google Code? Anybody remembers it? I mean, it was shut down 2015. 1,500,000 projects endangered. And many other things like this are happening. We do not have an archive for software. And finally, what we are missing is a research infrastructure. One of my best friends is directing the James Webb Space Telescope program here. In 30 years, $10 billion spent to actually look at the origin of the universe, something that I definitely love. How comes, as computer scientists, technologies we have not been able to put together a common open infrastructure for analyzing all the source code which is developed today? So it was urgent to take action, and this is the reason why a few years ago we started a project. The code name is Software Heritage, as software is our heritage. The mission is at the same time, humble and ambitious. We are going to actually look out there to collect, preserve, and make available all the source code of all software ever written. Only the source code, all the source code of the software ever written. It is not just looking at the past. It is, of course, collecting the history and the heritage of the software that has changed our world, but it is also building an incredible telescope to observe the galaxy of the evolution of software across the world. How would you do something like this in a long-term perspective? Well, it requires some thought. You know, I'm old enough. I made a lot of mistakes in my life, so I'm trying not to make the same, at least, to vary a bit the pleasure. So first, we need more people sharing the vision. You need an international, universal initiative. That's the reason we have a partnership with UNESCO and many other people in organizations supporting our work. This is important to raise awareness of the importance of this mission. And on the other side, this, of course, costs money, and I do not want to depend on a single donor or a single organization or a single structure. That's the reason we have a bunch of different supporters, starting from a national research infrastructure in France, which is called INRIA. I'm sure many of you know it. And then many different companies. And you know, there is a lot of white space there. So if anybody wants to join in, I mean, they're very welcome to come. And how do you do this technically? And why this is more difficult than any other archival project we actually know? Well, think about it. I mean, we want to archive all the source code ever written over the planet. Well, now you need to go and talk to GitHub. We are here, talking to them, happy to be here. But you also need to talk to GitLab, to Bitbucket, to NPM, to PyPy, to to Debian, to Red Hat, to many other places where source code is actually available. And unfortunately, there is no standard. There is no HTTP for the event feed on these platforms. So we need to build adapters for every single one of these and to be able to talk their language and list the number of projects which are on each of these platforms. But that's not enough. Then you discover that a lot of people use Git today, but you have tons of projects which are under different version control systems. Subversion, Mercurial, Bazaar, CVS, you name it. And then you have different formats for packages, etc. For a long-term perspective, we cannot just store a Git repo or just store a Subversion repo or just store a zip file. So we decided to go one step forward And we actually decided to translate the history of development of all these kind of different version control systems, all of these packages, all of these formats, into one single unified format, which is basically a gigantic Merkle tree at the scale of the planet. Think as a Git repository at the scale of the planet where everything is deduplicated. So this is actually building one of the biggest public graph of social production that are available on the planet today. It is 20 billion nodes, 280 billion edges. I can tell you for every single file you produce in how many places it can be found. Okay? This is an incredible source of information, and it only takes up 400 terabytes, because, of course, we are deduplicating everything. The factor of compression is 300. And then some milestone, and I will just come to the work of today. I mean, all this started in the summer 2015. Here we can see a picture of the first server in our data center. We went public on June 2016 with the first sponsors. In 2017, we've signed an agreement with UNESCO. Here we see the former president of the French Republic and many other, and the former director general of UNESCO on preservation of software. We opened the archive last year to the world, so you can go there. Please go there, archive.softwareazure.org. You will not be lost. The interface is kind of similar to the one of GitHub, but you cannot make pull requests, okay? It's an archive, not a development platform. And finally, in December last year, we opened up a mirror program to have copies of the archive under different administrative responsibilities all around the planet. And in February, there was a Paris call by 40 experts convened at UNESCO headquarters stating that software source code is important as a part of our cultural heritage. And if you look at what is in this Paris call, there was, for example, a call to support efforts to gather and preserve the artifact narrative of the history of computing and a universal archive for preserving source code over time. And I'm delighted to say that thanks to the vision that we have seen in GitHub today, we will be working together with GitHub on two things. One, improving the software heritage acquisition process, which is a process we published a few weeks ago, telling you how to recover legacy and unmark your source code. And we will massively improve the quality of our archival of GitHub, making it easier and sure that your repository will be archived regularly and quickly and will be available for a long time. So sorry for taking so much time, but you see, it's kind of a passion of me to be here with you and sharing this. If you want to know more about the project, just go to www.softwareazure.org or follow our Twitter handle as SWHeritage. You will see the link to our slides today, and looking forward to hearing more. If you are interested, I'll be here tomorrow also. Thanks a lot.
Thank you, Roberto. And the last speaker for this session surely needs no introduction, but please put your hands together for Brewster Kahle of the Internet Archive.
So I'm wrapping up today. And what I thought I'd try to do is give you a little bit of an idea of what the geek's view is and how wrong we've been about the issues around long-term heritage of this stuff. The Internet Archive, what we're striving to be is the Library of Alexandria for the digital age. But the Library of Alexandria is probably best known for what? Burning, right? For not being here anymore. Or it was the center of learning for 500 years, and it's just so completely gone. As best we can tell, there's 8 pieces of papyrus that are around today that were in the ancient library, right? It's just so frickin' gone. So it's a little daunting way of trying to view this, but you sort of say, okay, yeah, we're geeks. We can try to figure out how to get around this. So I'm Brewster Kahle, the founder and digital librarian of the Internet Archive, and I thought I'd show some of the different attempts that are in either my personal collection or the Internet Archive's collections of this sort of long-term heritage thing and sort of how is it going. This is cool. This is the Hyakumani Dharani scroll. So Japan, the Empress Shotoku in the year 764 AD. 764 AD was became Buddhist, was really into it, really wanted the sutras to last a long time. So she set out the challenge to make 1 million copies of the sutras, and it's a little scroll on the bottom. And that pagoda, that lathed pagoda, it's about this tall, is a cover. It's a book cover. So they made 1 million of these things, and they put them in 10 different temples around Japan. 9 of those are completely gone, but 1 is still there, and they have a ton of them. And they came on hard times at the end of the 1800s, and so they sold off about 3,000 of them, and that's one of them, which I'm kind of happy. We have one, it's actually not that one, but we have another one. But that was sort of an idea of lots of copies, keep stuff safe, so that's one way to go. This is a picture of that cool Rosetta disk from the Long Now, completely awesome and sort of about the size of it. You can sort of see how big it is. And it's a good puzzle. If you're trying to figure out, and this was something we did a long time ago, to try to say, spend a commute on it, or shower on it, or just sort of a friend's conversation around it. If you were trying to make something last a long time, you have 3 questions: what to put on it, what to put it on, and where to put them. And this is a really cool answer to it. And they say that it was my idea, which I think is true, and to do this, the Rosetta project, but it really was pulled off by the Long Now folks. Okay, test for you guys. Do you know what this is? It's a picture of. Microfilm, right. Okay, so it's a little, this was, during the 20th century, the idea of taking pictures of pages and having these sort of funky readers to see these old things was kind of an idea of universal access to all knowledge. And the medium was to last 500 years. And actually, it can. And unless it's thrown out. So this is a canister of print masters of the periodicals in the United States. So it's each one of those is a year of print masters. So these are the actual things that was then copied to send to libraries. So that's 20 years of some periodical. This is the vault, and if you look really carefully, in the center there's me. I'm in the center of that thing, and that's just one row of one floor of the vault, which went from University Microfilms to bought by Xerox, and then it was bought by Pitney Bowles, and then it became ProQuest, and they spun it off to NA Publishing, which went bankrupt, and it went into a bank and was going to be thrown away. So we bought it. So the moral of the story here is, yes, this medium could have lasted for 500 years if you don't throw it out. And so it's a kind of a lesson towards how to do continuity. This is a picture of the physical archive of the Internet Archive in Richmond, California, and it's basically indoors. It's books or records or whatever in boxes on pallets, protected by boxes, protected by shipping containers, protected by a warehouse, protected by nonprofits. So it's basically sort of, there's levels of shields to try to basically have this stuff last based on different forms of attack or decay or institutional problems or the like. So this is sort of an approach towards having things last. Then let's go for digital eras. That's a younger me. That's standing next to a tape robot. Okay, let's talk about terrible technology. Let's all talk about tape robots. Okay, so they suck, but they were able to get us to 20 terabytes of collecting the World Wide Web to become the Wayback Machine starting in 1996. And the ones behind us, we were dreaming of having a terabyte of spinning hard drive on these Sun microcomputer era things and other types of computers to be able to start to do books, music, video, web pages, software, and we've been working away at it. This is a copy of when the Library of Alexandria in Egypt, they made a new one of these libraries. They were inaugurating in the year 2002. We said, let's give them a copy of everything. And so we did. And it took up most of an airplane, and it's these computers behind it. And they re-architected the first floor. And they were celebrating this digital collection, which is really tremendous. So this is a picture of that era of, it was about 200 terabytes at that time of the Wayback Machine and the movies, which were the things that we had at the time. This is a picture of a shipping container. I hate building data centers. So we thought, why don't we go and make a data center in a shipping container? And then you can just put it places. You can put it outside. Sun ran with the idea. They credited us with coming up with the idea, which I think is true. And so they gave us one. And we put it on the Sun campus. And this is a picture from 2009 of the Wayback Machine. So I can answer how big is the web, but you have to ask me. How big is the web? The web is 20 feet by 8 feet by 8 feet. And it weighs 26,000 pounds. And that makes it 80 micrograms a hit, which I think is kind of fun. So that was the era then. And actually, I think it's about that same size now, given hard drives are getting larger. But we're off of Moore's law, so it's a little bit of a problem. This is the picture of the current petaboxes. So this is what we currently put the Internet Archive. This is about 7.5 petabytes of the primary copy of the Internet Archive. It's in a church we bought in Richmond, California. Please visit. And the idea is to try to have these. This is the primary part of the primary copy of about 50 petabytes of the Internet Archive. It costs about $1,500 per terabyte to try to keep a terabyte alive forever, right? So and that's sort of assuming still an exponential, and we really need some help out there, guys, to keep going on the decreasing curve so that basically it's a finite amount of money to keep data alive and going. But this is sort of our current approach, and we have not just the primary copy, you have other copies, and then Alexandria, Egypt, Amsterdam, Canada, to be able to have other copies or partial copies of this data in different places. But all of this, what I've learned is really the way to make things live is these things. People. And people that care. That really, at the end of the day, I don't think it's going to be a hardware hack. I think it's going to be people that care about the stuff. And this is a picture of the Internet Archive staff, and these are the folks that are caring at the Internet Archive. What is really amazing to me about this whole thing is GitHub cared. GitHub cared. That they said, we think all of the work that's going on, all the software that's being built on top of it is important to keep around forever. And when John Evans came to the Internet Archive and said, would you be interested in working with GitHub to go and make sure that this is permanently available in a different way than what they were doing with the others, we were just overjoyed, right? Usually we get to pick up the pieces after people go down. Or we try to do it but rarely do they think ahead like GitHub has. And where's John Evans? Can you come out? And I think it's amazing and rare that GitHub went and to the extra level to go and put together different solutions for how to make this whole thing happen. Hooray for GitHub. So what we're trying to do is archive the whole damn thing. And we think it's about 250 terabytes. We want it to not just be a sort of you're going to have these sort of in the vaults sort of approach. We're going to try to make it live. We're going to try to make it so that it's still there. You can check in and out. You can talk the GitHub protocols, but also be able to be used by researchers in new and different ways. If you want to participate in how this whole program works, please work with the Internet Archive, volunteer, help, work for us, donate money, any which way. Thank you very much.
Thanks, Brewster. And thank you to all of you for attending this session. We really appreciate it.
We're done.
I think we're done, yeah.